All right, let's share my screen. Can everyone see that? All right, amazing. Yeah, I'm super excited to talk about local first to an audience who's probably already heard before what local first is, and this is not the first time you're hearing about local first. I'll still include like a small motivation as well, why I think local first matters to more people than might think so already. But yeah, and specifically, I want to talk about the local first state management, the local part. But yeah, maybe we've interacted already at some point in the past. I've been like dealing with DevTools for quite a while now. Always kind of like going back and forth, like using DevTools, then thinking, okay, maybe some things could be better. Sometimes I'm building DevTools, and like it's kind of like a perpetual loop. So in the past, I've like created Prisma, which was very much focused also on state management, particularly database tooling, typically more on the server side. And I'm currently building a music app in a local first way. And besides that, I'm also doing a bit of open source consulting work and R&D. Yeah, so I think we can cut this talk actually pretty short. And this is like the TLDR on my talk. Like, please avoid distributed systems if you can. If we want to extend the talk a little bit, then I'll give you basically the same pitch, the same talk twice, once on a macro level, why you should avoid distributed systems on a macro level, or deal with them in the most bearable way. And then also on a micro level, which is the local state management part. So, but basically, I've just come to the realization today that I'm giving the same talk, the same pitch twice in the same talk. So yeah, in this talk, I'll do a quick motivation on why local first, which is basically the macro part of distributed systems. And then I'll talk about the local first state management part, which is the micro part of the same idea, basically. I want to contextualize this with saying that have like most of my development background is really around like web development. I'm pushing further and further into what I think is rather like native app development, and I'm finding myself in a situation where I'm bringing those practices to web development, and I've been doing the vast amount of my development efforts kind of like around the React ecosystem, which I've been using since I guess like 10 years now, which is crazy. And so a lot of the the learnings I'm sharing here, or like my approaches, they might not fit all the possible use cases and all the possible apps. It's like really I'm trying to share my learnings here that I've come to by working on this particular music app, particularly for local first state management, where you really try to keep a lot of data locally. This is a good fit for a music app, but I think actually a lot of apps, more apps than you would think, are a good fit for local first. But yeah, that is I'm sharing this approach, and I'm also to make things probably even harder for myself. I've kind of found this weird obsession, or found out that I have this weird obsession for high performance. So I'm trying to turn this app really into a really well-performing app where I care a lot about like render speed, etc. And I try to keep the web app aiming for 60 FPS or like 120 FPS. Not sure whether PVH is here, but I think I've overheard PVH saying once like a quote of like next frame or money back. So that's kind of like my mantra for this app development. And so yeah, I won't actually, given is not as much time today, I won't actually have the time to go too deep into Overtone and like how the state management part fits into Overtone. So I'd rather try to extract out the ideas and sort of principles I've ended up while working on Overtone. in a more general way. But yeah, for the last 2 years, I've been working on a new music app that tries to, it's kind of like a universal music app that tries to bring together all different kind of music sources. So I listen to a lot of music wherever it might be, on SoundCloud and Spotify, YouTube, Bandcamp. And I'm kind of tired of having always like 20 tabs open of wherever the music lives. So I'm trying to tame a bit of that aspect of the internet and trying to build a really, really nice premium music app. So if you're interested in that, I'm planning for early access later this year. But yeah, so just wanted to give this as a context that all of my learnings or insights are really contextualized around this. So what follows is anecdote that I've had multiple times myself, and I've seen a lot of other similar anecdotes happening, which is something like this. You want to build an app. Maybe you build it yourself, maybe you build it in a team. And so let's say you build a web app, let's say you build a mobile app, maybe with React Native, doesn't really matter. So you build it in this more like traditional way, like often like a street tier architecture. If you want to make life even harder for yourself, you do microservices. And so you have like your app, front-end app, you have a database somewhere where your data lives, and then you probably put like an API tier in between. And so while you build the app on your local host or wherever, or you deploy it to your nearest data center, the app's working somewhat okay, and you push it out, and for users, it's actually okay. However, turns out that some of your users are living further away from the data center, or for other reasons. Turns out that the app gets pretty slow, and the user experience is bad. So as a developer, okay, what do I do about a slow app? Probably the data that comes in too slow. So we know how to fix that. We fix that by introducing caching, but we also want to make things faster when you, like, let's say you click a like button, you want the reaction to happen immediately, the thing that, for example, GitHub doesn't do, but probably should do. And you introduce optimistic updates. So you've kind of like taken on that burden as a developer, and you now have to, like, you've practically introduced like this little mini cache database inside of your app, but was all for a good cause, since your users are happy again. However, won't take long, maybe particularly if you build a mobile app that you want to use, you have your phone with you, you might just like leave to go on the street, and while you go off the Wi-Fi and you jump on mobile, like there's actually a time where you don't have connectivity, or you're on a plane, on a train, whatever. This happens more often than people would actually think. And the app just becomes completely useless, and you can't access any data that just like 30 seconds before you actually had access to. So how do we fix that? Well, kind of just more of the same. We basically just slap on more caching, slap on more optimistic updates, and the database in our app is like growing and growing. So the user is happy, developer probably not so much, because you already start fighting to, like, you start to fight sort of like state inconsistencies. The tax you always have to pay about caching is cache invalidation. And yeah, so life gets pretty terrible for a developer. And yeah, as the app matures, or as you get more and more users, maybe your users have also now higher expectations for the app. And let's say a user wants to collaborate with other users, maybe just with themselves by using the same app on desktop and on your mobile phone. And let's say you have a user who is editing some form of like a document, could be anything really. And so that user now like pushes, like makes a change. And let's say another user is editing something at the same time. And if you have not purposefully designed for that, now there might be conflicts, like the line you've been just editing like disappears under your cursor. Really terrible user experience. And so yeah, now like how do we deal with this as a developer? We've kind of like, when we're starting from this 3-tier architecture, we're basically learning, okay, we didn't really design for this, so we have to do something now that feels very different. But yeah, we try to like retrofit syncing into this system that was really never built for this like entirely different way of like how data flows. And so I've seen like this journey like multiple times, and that's not fun as a developer. Like as a developer, we've just like racked up years worth of tech debt and really pitted ourselves into a corner here. So the problems that we're dealing with is like state management has become like super complex. We're fighting cache invalidation problems left and right. We also, like, while trying to mitigate things with caching, we have like inconsistent states when the optimistic updates don't go right, and the data syncing flows is really like doesn't really fit with the 3-tier architecture that we've built before. So we're like, yeah, we have so many all of those problems basically originate from the fact that we have like here, we have like a database now, like pretty sizable database here in the client, and kind of like the main database on the like somewhere else. And so we're really like dealing with state that's distributed. So that's observation 1. And observation 2 is where we've tried to like introduce this little caching thing in our app that has now actually grown into a full-size database. So I want to dive deeper on both of those observations. And so the first one, I've actually come across an interesting quote from someone's blog where they said, when I've worked on any kind of distributed system, including systems as simple as a web app with a front-end and back-end code, probably upwards of 80% of my time is spent on things I wouldn't need if things weren't distributed. And this deeply, deeply resonates with me. So this would be now like the macro pitch to the world who haven't yet had their fair sip of the local first Kool-Aid, is to solve like that entire distributed systems problem by trying to orient things in a local first way. That means you get to like solve these problems like somewhat separately in a much more intentional and principled way. So you're trying to basically organize things in a way that you think about syncing data. That's the distributed part, and then you can fully embrace the local database that you've now like actually you ended up with this database anyway. So let's embrace it. And so that is the second part now of my talk, where I want to talk about like how to do this. If you want to learn more about local first, it's probably been already shared a bunch of times, but I can highly recommend this article. And to quickly share my pros of like why I think local first, people should care about it, both users and developers, is for users, I think they just get better software. Like it's actually a really interesting like exercise you can go through, is like just look at the apps that you use on a daily basis, like whether it's now Discord or whether it's like your Office suite or like different apps. I think if they were like more local first, and local first is kind of like a spectrum, I think you typically get faster apps. You get apps that are like almost always available when you're offline, when you have poor connectivity. You have much better longevity, so that the thing you had access to today, like these tools, like a lot of those might go like bust in 2 or 3 years. Your data is gone, you can't use the tool anymore. It's much easier to build collaborative apps in this way, and you also get better data privacy. And if you haven't fiddled with this, you might actually think, okay, we're buying users like all of those benefits, but for developers, it's probably now even harder to build apps. But I would actually say, no, we get much simpler architecture. We solve the distributed systems problem in a sort of like a contained and very principled way. And overall, like there's really, really nice developer experience benefits. So it's easier to develop, easier to test, easier to debug. And this is not just like some marketing slide now. This is like my reality for the last 2 years. And that's been really amazing to use. So yeah, this was like the macro part for local first. I want to now talk more about the local first state management part. And I actually don't want to talk about syncing that you might do like using CRDTs, etc. I also don't want to talk about like other problems such as like versionings, migrations. All those are relevant problems that someone else should probably do a talk about in the future. And also like how you integrate with other APIs with your local first app. But what I want to talk about is the local and local first, and particularly the state management aspect. So if you build a React app today, this is where your state management story kind of starts, that you have, maybe you just use the React use state primitives, and you work your way forward from there. So if we look at that and think about the domain of like local state management, I've like had done a lot of experiments. I've tried out a lot of different like existing solutions, and some worked better for me, some didn't work as well. So I've started to think about like what are some of the like goals and requirements that I want from such a local state management solution. So I started to like over time, I think I distilled a set of principles, a set of goals that I want to share with you today and motivate why. And that's probably the most important takeaway for you, actually, that maybe I can nudge you in that direction, that you see the benefits in those, start embracing them with your app that you're building, and hopefully we can have more state management solutions that follow these goals in the future. So one that I think is really important is that it should be easy for users and for app developers to have persistent state. I think mobile apps today do that better than web apps. I think a web app, you like fill out a form, you reload the app, and like poof, everything is gone. Like I filled out like insurance forms, whatever, like it took me like half an hour and then something crashes, everything is gone. It's terrible. I want persistent state basically by default, pretty much everywhere. I also, as a developer, I want things to be reactive, particularly my state as well. I want my state management solution to help me with transactionality, and I want things to be super fast. So let's go deeper into this. Persistent, already talked about it. The goal is that the state, UI state, pretty much everything that's important about the state of the app, your expectation of a user intuitively, I think, is that things should be persistent. Like if you have a real world analogy and like you have a room with a table and you put something on the table and like you leave the room, you come back, you'd expect the thing on the table to still be there. Like most web apps today, the thing is gone. It's kind of weird. So I think for users, it's a much better experience. There's no data loss that removes the fear of like you're investing into filling out a form or whatever. And like, I think that would make a huge difference. And for developers, that's actually an amazing development experience when your state is just like much more introspectable. You can also, it's much easier to debug something. If your entire state, including like navigation state, scroll state, etc., isn't that like database, you can now like download the database, introspect it. You can even like upload it again to reproduce a particular state a user might have like some errors with. That's amazing. But yeah, there might be, if you were to now say, okay, yes, I want to make things persistent. How do I do that? Do I do that with like local storage or IndexedDB? It's actually non-trivial to implement that without like suffering from like a performance overhead. You need to think about, okay, now the state that I have in memory need to serialize somehow, that I can read and write it from that data source. Maybe I need to migrate things. Yeah, those are fair challenges. Then reactivity, the state should be reactive. So what we had before with React use state, that thing is kind of reactive, but now we want it on a more on a global level, basically. And if you think about it, like you have a SQLite database, that thing is like not reactive at all. Like if you have a query that maybe has the user count and somewhere else you enter a new user, now you need to somehow like make sure that that count query is updated. And you want to do that with like as little as necessary, but also like as little as possible, but as much as necessary, so that you don't have stale state somewhere. And you also want to couple that with your view rendering layer so that you re-render as deep down as possible that React component. Then transactional consistency. This is basically that if you change something somewhere in your app, let's say we have Twitter and we click on like that, and the same tweet is somewhere else in the app, you want the like button to like pop up at the same time and not like not after each other, since otherwise you kind of like have the same distributed systems problem, but like in your local state management again. So you need to deal with that somehow. Or to contextualize it with the Overtone app I'm building, this is where like what you want from a music app is like playback music. So when you press play somewhere, you might actually also have like a play bar, and you want to have the play button reflect the playback state at the same time. You actually also want to have like hear audio. So if things like race and are out of sync, that's like a terrible user experience, and can be also like really, really tricky to work around that as a developer. But to do this properly, you need to track those data dependencies across the entire app. When you write something, you might want to like you want to do some changes like transactionally, and to put all of this into like a simple and ergonomic API, that's actually quite challenging. And then to make all of this worse, we want to make things fast. So and having like a fast state management solution, that might be like might mislead you while you do like your hello world that it's fast, but that it actually scales to like hundreds of thousands of records with like complex queries across the entire app, and to combine all of the previous goals together, that's actually pretty tricky. So yeah, those were like the main design goals I had. And as we've been experimenting with different approaches and different APIs, we've kind of like still we're kind of like always stuck on one aspect, is like whichever database we experimented with and like tried to build a layer around, this database was typically always like asynchronous. So here this is just like a very simplified use query React hook. And so that's kind of gets you the gist that you have something that's sync here, but you need to do the async part somehow like in use effect. And now you're just returning like a loading state and the actual thing. And now this thing here where you need to always like branch, hey, is the thing loading? If so, show a loading spinner. That's like almost like a cancer throughout the entire app. And this, while here might still seem fine, but if you have a lot of complex app state, and like you have multiple queries across your entire app, now you need to check like, oh, if the one thing is loading, so you have this combinatorial explosion of like how you figure out like all of these branches. And so it started to like it dawned on us, could we actually like have one additional goal, and like would it be crazy if we can somehow like drop the async and the await here? And this was kind of like a crazy idea, and it really like we've been now like working on this for like 2 years, and for the first year was really like our existential question, like, is this even possible? But we've been pretty convinced that this is worth pursuing, and ultimately it started to pay off big time. So that's kind of like our secret sauce here, about what we propose for local state management, which is make as much stuff sync as possible. So basically the goal is here, declare and declare and resolve your queries synchronously. No async, no await, no loading state. And that's like for you as a developer, massively simplifies the application code. Kind of like that solves the distributed systems problem I've mentioned earlier, but like locally, which is like kind of crazy if you think about it. That like if you the way how you normally build a web app locally, where you use like IndexedDB, etc. This is where you have like a local version of the state, the same distributed systems problem, where your React state is in one state and like the database state is in another one. Now you try like to bring this together, and all of that is kind of like sidestepped if you can make it all like simple and nice through synchronous queries. But obviously, the database needs to support synchronous queries. SQLite kind of does, and we did use SQLite for this in the past. However, now when you do it sync, you need to bring it in the same thread. So like typically in the UI thread of your app. And now that means if a query takes too long, it blocks the entire render loop. And performance-wise, this can make the user experience much worse actually if you were to compare it to like async. So you really need to get this right, and your whatever you use as an underlying database needs to support this, and that's really tough. But when you do it and when you invest that, I think it pays off big time, and that's actually how you get the best possible performance. And it's very similar to how game development works. So yeah, oversimplified takeaway for you here is like for local state management, if you can go sync, do it for your API. So we've looked at a lot of different solutions here with like React State, like Mobex, Redux, Zustand, all of those things, and I think they're all like obviously contextually from the history one like learn from the other, and like everything improves sort of upon of each other. But none of the things we found so far really satisfied all of our goals of like keeping state persistent, reactive, transactional, fast, and providing the synchronous query API. So yeah, and that has led us basically to, over the last 2 years, fiddle with that thing what we called Riffle. And so by we, I mean another person, like 2 collaborators of mine, Jeffrey Litt and Nicholas Schiefer. Those 2 have been working at MIT and doing their PhD thesis actually about this entire topic and Riffle. And so I've been coming and joined them on the research project of Riffle as the app developer working on Overtone. That made an amazing collaboration. So the concepts that we've basically established here is to have a reactive query graph with like all of the goals that I've motivated before. And so you can kind of see this now as like this sort of like a stacked 3-tier architecture, but all locally and all in a single thread. Is that you have like your React componentry on top that can express, in there you can express queries, and queries could be either like SQL queries. We actually also support GraphQL queries, and you can also extend those with JavaScript. That's the Riffle layer, and that just mediates and integrates with React and SKDB. And SKDB, as mentioned before, like to make synchronous queries happen and keep them really fast with all of the goals I've motivated before. The only database that really allowed us to do so is SKDB. SKDB is kind of like semi-public. It's not yet really publicly available in a way that you can use it off the shelf, but that's coming soon. And so yeah, SKDB is developed by a bunch of really smart ex-Facebook engineers using its like own custom program language called Skiplang. Kind of wild story for another day, and I would actually love to talk about it. But all of those technologies together is like what is the foundation for Overtone's state management, and that I basically wanted to motivate today. So we're running a little bit out of time, but I wanted to quickly give you a demo to prove that the thing I was talking about actually works. So I'll just like open here a new tab. And so this is a super simple to-do MVC app using Riffle and SKDB. So yeah, I am currently giving the talk. I can also say smart things and do the demo. So this works. I'm doing the demo, and I can also like filter things by like active or completed, show them all. And so this entire state here, like just to quickly show, like it's reactive by clicking around. It's also persistent. So when I reload this, it was it was there immediately. I can also, if I, for example, show the FPS meter by just now, like, to make more room here. Second. So if I'm clicking around, this is typically in the next frame, so it's fast, and there we're still working on performance improvement as well. And what's kind of like the cherry on top is that this entire state here, you see it here, we actually have like this little Riffle debugger as well. So we see the tables that back this, and you see like that even the UI state itself is just like part of the database. So when I'm writing something here, it's like directly reflected here. We see like live queries. Live queries is, for example, the currently visible to-dos. So when I'm going here, visible to-do, you see this here. If I go to completed, you see this here. So it's like super nice to work with here. It's just the basic concepts that you would expect from like a SQL database that kind of like magically fuse together. So yeah, I would love to go deeper on this another time, but going back on this on my slides to wrap things up. Briefly summarizing the concept that we've seen here. So at the bottom of this, we basically have like SkipDB, which you can think of like a next generation smarter SQLite with all of the properties I've mentioned before. That's reactive, like persistent, obviously, but also like transactional, provides synchronous queries, and most importantly, that provides the performance. It does so through incremental view maintenance. So that is, sorry, jumping back here. So the foundation is basically just tables, and then Riffle sits on top of that, where you can define queries. And queries can be SQL, it can be JavaScript, and those can depend on each other. And this is basically just put like as a computation graph, basically merged together and then connected to the UI, and that makes the state management work. So I quickly want to show you how that looks like in code. This is the simplified to-do MVC example, but we basically just define a schema here, like you would do it with like SQLite, for example. Here we just define the to-dos table. We have some other tables here as well, and then we can define actions. Actions are like very simple, like indirections basically for writes, just that you have like all writes in one spot. And then you take that schema and provide it as a React provider here. You have some way how you can do the state initialization here. And we also have a way to define like some queries that are useful across the entire app, for example, like the UI state here. And yeah, and that is basically how you use it in your React code. So here, for example, we can simply use a query where we simply run a SQL select query, or you could also do like a GraphQL query here, and you get it back synchronously in the first render loop, and that's magical. And the writes are just as simple. So you basically just you take like the Riffle store here and you apply those events, and those events are basically just an indirection to this. Then it mutates the SQLite data, the SQL database, and in the next render, like all of your state is up to date. So yeah, so sorry to be the bearer of bad news. I wish I could tell you that Riffle and SKDB is something that you could like use today, like for your own apps, play around with. We're making progress there, both on the Riffle side and SKDB side. But at the very least, I hope like sharing those design goals in the first place could already be useful for you. for your own apps, and maybe also inspire like some of the other state management technologies out there. If you're really, really keen on getting your hands on Riffle or SKDB regardless, because like it seems like the perfect fit for the app that you're working on, feel free to get in touch with me, and I can see whether there's like some way to collaborate or to hook you up with early access. In the meanwhile, there's also in Riffle.systems, there are some essays about Riffle, and there's a new one coming fairly soon. But I think there's a lot of this is like highly researchy and like very very experimental. So I think there's actually right now some alternative technologies that might not provide all of like that might not satisfy all of the design goals I motivated before, but they're probably a bit further along that you can build something with it right away. So I can point you to those, and I invite everyone to share like their technological favorite as well. But yeah, hopefully more on Riffle and SKDB soon in the coming months. And yeah, I want to leave you with again just begging you to avoid distributed systems problems as much as possible. Solve them on a macro level through following the local first approach, and on a micro level, I think the principles that I've motivated here for local state management, this is what I've had the best time with developing with, and I think what is a great foundation to build great apps for users. And if you haven't so far, yeah, give local first a try. Try to build an app with that. And yeah, without more words, thank you so much for listening. And yeah, if you have any questions, I'd be happy to answer them right away or follow up with me. Thanks so much.
Thanks, Johannes. That felt like a masterclass on like the issues with React, plus why you should do off local first, plus two stacks on how to manage local state. I'm a new React Native developer, and sort of the patterns that are being described for like stage gating, if apps booted up, if users signed in, if whatever, like definitely feel the combinatorics pain. Next up, we're gonna have Lewis come give us a talk, and his topic is on data sync strategies for the working dev, which is perfect segue from Johannes's talk, since he
Yeah.
didn't really cover some of the sync issues that you'll run into. And without further ado, I will hand it over to Lewis.
Okay, we have audio, we have video.
Yes, sir.
Great. So I'm going to give a talk about practical conceptual knowledge for the working dev. It's actually going to be almost the opposite of what Johannes said. So some respectful disagreement within the community, but here we go. So inside the local web dev community, there are two wolves. By the way, I hope you guys like old memes. This is full of old memes. So there are two wolves in the local web dev community, right? The first wolf is completely focused on end user products. It's a bigger business like wolves. You want to cast aside all this network dependency, and you kind of wish all this annoying theory would go away so you can just go ahead and make your products. And here's me in that mode. I was working for an agritech startup, and I'm out here in a cattle farm with no internet, learning how to deworm cattle. So really getting into the practical side of things. There's another wolf. The other wolf is more of a theoretical wolf. They often make tools that other people can use to build products. They eat distributed systems papers for breakfast. They consider order theory to be light reading material. And they try their hardest to make the product-focused wolves not have to think. And here's me with a stage photo of all the things I'm trying to read so I can appear really intelligent on social media. That's me on that side of the equation. But I can't help but wonder if we're doing things a bit wrong local first. Can those with a product focus really get away with not knowing any theory? Should those building tools really be providing users with a one-size-fits-all solution, just in case product devs recoil at the idea of having to think about this a bit? I mean, let's take relational databases as a good example. Your average senior dev is not reading papers on relational algebra. They probably can't implement a high-performance B tree, and they typically don't recite passage from CJ Dates databases types and relational model to random MongoDB users they see. but nor are they exactly ignorant. They have a good working knowledge of SQL, they understand about views and foreign key constraints, and they have an idea of when to denormalize and when not to. So I think that's the missing link we have in our community. There's something between the small, thankless tugboat of academia and the giant lumbering cargo ship of industry being led to safe harbor. I put it to you that local first web needs not just product pragmatists and theorists, but also a good conceptual knowledge across the board. So here is a spicy take. I know a lot of you work on turnkey solutions, one CRDT to rule them all, where you do best to hide the merge semantics from your users, lest they be forced to read research papers from INRIA. But as a full disclaimer, I do respect the work that you're doing, and I'm happy to be proven wrong on my little theory here. But as it stands right now, I have these lingering doubts. So can product-focused developers really treat syncing as a black box? Is there really a silver bullet we can all use? I say there isn't. Different syncing strategies have different trade-offs and produce different results. Let's let users decide what's best for their app. So I'd like to start off a bit with talking about conflicts. And I really love this quote. It's from the old O'Reilly CouchDB book. Conflicts occur in distributed systems. They are a natural state of your data. I want that to really sink in because we live in a kind of mealy-mouthed world, and the term conflict sounds alarming. I mean, after all, companies don't kill off products. They sunset them. Beautiful sunset. Isn't that nice? Likewise, there's nowhere you can find old, crappy software in our industry. Instead, we have a rich legacy of previously loved systems. And of course, modern companies are now incredibly sleek and aerodynamic. Why, I hear you ask? Because we've done away with the anachronistic practices like cost-cutting. We streamline instead. So against this backdrop, the concept of a distributed systems conflict might make you afraid. Don't be afraid. It's perfectly fine. You don't have to think of them as conflicts. You can think of them as opportunities to eventually merge. But what do conflicts and merging conflicts look like in distributed systems? First, let me talk a bit about events. So events are pieces of data that are immutable. You can't modify an event once they're created. They're append only. You cannot remove an event. And they're facts. They are a thing that definitely happened. And a great industrial use case for this is Kenny Sabeer's article about implementing event sourcing for apps deployed in remote rural Australia. By the way, Kenny, if you're listening to this, I'm still waiting for part 3. So with that thing with events about our mind, I'd like to do a quick technical demo against all professional advice I've received. So let's see how this goes. And let's think about we have a local node or a remote node, and let's say local node has an event B. It's also going to A, B, and that's also going to event C. And then our remote node gets X, Y, and Z. And what does this look like when we merge them? It simply unions the two events. Because, like I said, events are facts, they're immutable, and they're append only. Now, there's some complications here with timing, of course, and ordering them, but that's a bit beyond the scope of this. So that's one sort of easy example of how merging works, and it's a good conceptual model to have. You're simply append only, and you're appending the events from all the different sources that you get, whether they're recorded online or off, right? The other thing I want to have a quick look at is the multi-value register, which is, again, a very scary word, but it's 40 years old at this point. Originally came from a paper from 1983. It was also in the original Dynamo DB paper from 2009, and it's actually quite an old concept, actually, one that's not too hard to understand. So let's say I'm editing a value. Let's say it's an article, or it's my favorite animal, right? And I write cat, change my mind, I write dog, and then in another node, someone says the best animal, the best pet is a hamster. So we have a dog and a hamster. How do you merge a dog and a hamster? That's not like a Frankenstein question. What you do is the state of your data is now simply two things. It is both a dog and a hamster at the same time until you decide to resolve what it actually is. So this is the idea of versioning data that conflicts, which a lot of you will be familiar with from Git. This doesn't have a full history like Git, as of course your database would get very big. But it's a similar concept. Here, essentially, our favorite animal is in conflict And to merge the conflict, we could override it with something completely different, like a rabbit. And then we could sync that here. We still haven't synced there. So let's say both nodes agree on pony. Pony here. And there we go. We've solved our conflict as both nodes agree. So that is a very basic way to do it. And of course, you don't have to display this as a UI question. You can also use this as just a mechanism to detect conflicts and do something quote unquote intelligent to resolve them. Okay, that tech demo went off without a hitch. Back to this. So both of these are examples of CRDTs, and here's a very scary picture from a CRDT paper, right? I think CRDTs are fairly misunderstood. I know I definitely misunderstood them. We tend to talk about these as if they are a library or a single concrete data structure, but I would try and get that out of your mind, because the deeper I go, the more I realize everything in this space that works is secretly a CRDT. A CRDT can be a single record in the database. It can have CRDT semantics. The entire database itself can have CRDT semantics with the way you merge it. So again, don't be intimidated by the concept of CRDTs. They're kind of a set of rules that allow merging to happen in a way you can reason about. They're almost more of a design pattern and less like a library that you download. And I'm going to go a little bit off on a tangent to finish this up. I think it's kind of relevant, so I'm going to go ahead with it anyway, because one of the reasons I think it's very important for us to start bridging theory and practice is because our industry, as web devs, is changing very rapidly. Because since 2020, everyone has been talking about edge. Sorry, I mean, since 2020, everyone has been talking about edge functions. For whatever reason, a few years ago, people suddenly remembered users like fast response times, and they came up with a sexy new marketing term for machines close to the user. And edge became the new cloud. And, companies like Vercel and Cloudflare have been pushing edge services to the market, and everyone's talking about it, right? So, as someone invested in serving data not from servers close to the user, but from the devices in their hands, as in local first, I find all this edge talk almost a bit suffocating. I think I need a little room to breathe because I'm one step closer to the edge and I'm about to break some preconceived notions of what low latency really means. Because we who do local first, we occupy a position edgier than these edge people could ever dream of. We read and write data from a user's device first. How much edgier can you get, really? So while other web devs may play on the edge, we are the ones who rule the domain of the edge. We are the edge lords. Thank you very much for watching.
There we go. Thank you. Managed to come out of the dark. Let me just, there we go. Cool, and I shall try to share my screen. Okay. Do you guys see that okay? Yep. Cool, so yeah, I wanted to focus on some particular challenges around local first development that are in a way associated with our particular pattern that we're kind of working on with Electric SQL. And I've set up the kind of talk to maybe end on some discussion, so we'll see if that kind of works or if there's time. there is also a demo if you fancy one, and if there is a demo, then there is an audience participation element to it. So I warn you now. But to jump in, so basically I normally have a few slides ahead of this where I explain what local first is, but luckily I don't need to do that in this context and after the last two talks. But what I want to do is just sort of show you like the particular approach that we have with Electric SQL to local first. So we have this kind of Hasura for local first approach, where the idea is that you drop on Electric SQL on top of Postgres as a kind of, at a minimum, as a kind of management and control plane. And then you can, it basically gives you magic local first data inside of your client application. So you can build local first from the perspective of having your application code talk directly to the local database. You can also control where data syncs across your topology, so data can stay local, or it can sync through the cloud where it syncs through this Postgres database. I have a couple of little pictures that sort of demonstrate that. So we basically have this Postgres kind of in the cloud. We have an Electric sync service component. It's an Elixir service. It's not stateless, but it is rebuildable from the databases, and it's horizontally scalable. And then applications connect in for replication via the cloud through the sync service. And with that, there's a couple of kind of things to note. One is that you have this ability to publish content from the Postgres database onto the local applications, and you have the ability to aggregate data back from local applications into the central cloud database. As well, the Postgres functions, as I say, as like a control plane for evolving the database schema, and also we sort of extend the database schema with rules that control things like where data syncs and authorization and validation and so forth. So that's our kind of particular pattern. What I was going to do now, if it seems interesting, is maybe just jump out and kind of show that. We have a kind of, we have a slightly silly demo that we made. What I would do, so what it is, it's basically a Phoenix application that writes data into Postgres. Actually, I'm just going to show it in the web browser because I didn't get around to finishing up the styles earlier in the week for the Expo app version. Just to show you the kind of code to give you a sense of what we're going to run. So you basically have like a client and a server app. So on the server, it's a Phoenix application. It's like many others. You have, for instance, a data model here, and then that's kind of managed with migrations. For this particular app, what it does is it hoovers up, it basically synchronizes GitHub stars into a Postgres database. So there's like a worker process that does that, and there's like a webhook controller that kind of that writes the data into Postgres, and it's all kind of fairly standard sort of backend stuff. Then what happens is the database schema comes through the replication pipeline, and we build out a Prisma schema with it. And then the Prisma schema, we turn that through a generator into a type-safe TypeScript client. So the database schema that your client application works with is basically driven from the central Postgres. And then in here, you basically have, this is a React application. This is the little bit of kind of shim that's basically required to integrate I see the comment there from Johan about Prisma. Yeah, I agree. This is the little shim that integrates kind of Electric, where you basically import these generated models as your database description. There's a bit of config for where to talk to. You basically make some React providers, and you instantiate a connection to the database using whichever driver you want for your environment, and then we add some reactivity stuff on top of that. So this example uses WASQLite, which is a nice web WASM SQLite build that stores either to IndexedDB or to the Origin private file system, depending which is available. And then it just sort of works basically as a React application. So here's one of the widgets in the app. It's for adding beers. You get a handle on the electrified database. you can bind live queries to a React state variable, and it's type safe. So basically here, for instance, this client knows the structure of your database, so it kind of gives you hints in your IDE and in your build tooling. And then these results, just as Johan was showing, stay in sync, no matter whether you change the data locally, whether somebody else changes the data and it comes in over the replication stream. And here's an example of, for instance, you insert a beer into the database, or you clear all the beers, and then it just renders out a component. So I'll just sort of fire it up to give you a sense of it. I'm going to use ngrok to basically have some webhook stuff come in. I'm going to run our stack here, which basically runs a Postgres database. We use this vaccine system to do CRDTs and causal consistency and replication, and we run our electric sync service. So you can see if I go here, I can just connect into the Postgres, have a look. I ran the migrations before, so we have like a beers table and a stars table. And the silly idea behind the app is that we went to a conference and we were giving people beers if they starred our project. So that was where the kind of concept came from. So here we have a back-end application which receives webhook notifications. And then I can come and I can just fire up the front-end application, and I'll open it up in a couple of web browsers just so we can see how things sync. So here it is. Here it's empty. Now, basically, that's a local first application, and you can just interact with it, and it doesn't have the network on the interaction path, and it's naturally real-time multi-user. But what we do as well is we have this sync between the active-active replication between SQLite in the browser and Postgres in the cloud. So if, for instance, here I run a command to sync stars down from the GitHub API, that's going to come and consume stuff. These sync in batches of 50. Didn't actually do the work to base 64 the image, so that one kind of is why it's slightly laggy when it loads in. But as you can see, that's just basically synced data into the database here. If I now count the number of stars, count ID, select count ID from stars, live coding, 448. If I do the same from beers, we haven't got any yet. Now what I can do with the application is I can come and I can pour a beer, and then I can allocate beers across the different applications, and everything just syncs up. If I now select count from beers, you can see that there's 2 beers were created there. If I insert into beers, let's say ID, values, gem, random, UID, you can see that it just instantly appears in the local apps. So this is how you can use Postgres in a sense as a publishing system and sync data back and forward between the two. And for example, I've got another task here where I can say, right, everybody who started us gets a beer, and that just basically runs through and creates them. And you can see that it just updates everybody at the same time. The listings are just a maximum of 50 at the moment. That's why it only shows that. Yeah, so I hope that just gives you a bit of a sense of the kind of particular pattern that we have. As I say, the user experience inside the app is basically that you don't have the network and the interaction path, and you're working directly with an embedded SQLite, and you have this reactivity system. But optionally, if you choose to, you can sync data to and from the local SQLite and the cloud Postgres. I will hop back into my slides. So with that sort of pattern established, I wanted just to talk about some of the particular challenges that we've been focusing on as a project. And in a way, it's going from this core active-active replication into trying to make a platform that people can use to make applications that provides a realistic development paradigm. There's a whole bunch of other stuff that's involved in that as well. And there are other areas to potentially optimize that we haven't focused on so far. But these are some of the things I wanted just to kind of flag up that we've been focused on. So the first one is just to sort of just to skip through a couple of obvious things. So with local first, when you're building applications where you might typically have had a back end doing things like kicking off background processes, sending emails, etc. You either have to do that from the client, where it's tricky because you don't necessarily have the credentials available, or you have to translate your app to an event sourcing pattern. So you work off database change events. So there's a couple of examples here for doing it off a job queue, working off Postgres logical replication. You can put on a system like Materialize, which is just, say, super powerful to kind of run off Postgres, where you could then wire the events into basically any system that you wanted. Then one of the other interesting areas is that you've kind of, again, you've lost this trusted execution environment. And so you've kind of lost where you would normally enforce your authorization or kind of validation code. So stuff that you might typically write in like a middleware, you end up having to move into database rules. And that's been done by a bunch of projects in the past, like CouchDB, like Firebase, etc. And we have a particular rules-based system, which you can see on the right here, where you define those rules as extensions to your DDL specification in Postgres. Now, in particular, we don't just do row-level security, because what you really want to do is to be able to transpose the kind of logic that you would write that is contextually aware about the current client and authentication status. And you also want primitives to be able to express like the type of things that you typically do in that kind of code. So we have a slightly different system where we run, where we define the rules in the DDL specification, and then we write those into data structures in the database. They stream through into our sync service, and we actually apply the authorization logic within the sync service. So now that sort of brings me to kind of what I really wanted to focus on, or sort of introduce in a way, was some of the thinking we've been looking at about different ways of doing partial replication. And so you have this pattern of having like a larger, potentially central database in Postgres, and then you're taking potentially subsets of that data and syncing it onto the local applications. And if you kind of look across this slide, like I think this sort of gives a picture of the sort of type of range of models. Like ephemeral queries on the left-hand side is probably closest to like a traditional client-server application. You query the back end and you throw away the results. Like a pinned query system is one where you would say query the database, but then you keep the information around so that you can, for example, see data that you've seen before. A live query would extend that, potentially keeping those results in sync, but still just showing you the information that you've previously requested. Beyond that, on the far right, you have whole database sync, which is, for instance, what we implemented on our first version of the product. The simplest thing you can do is just simply syncing the whole database. But the content-based sync and the schema-based sync are the kind of interesting areas where you have not just about, in a sense, caching data to view it offline, but you can sync in larger chunks of the database to enable proper interactive offline use of an application. So for instance, you could potentially navigate to new screens that you haven't seen before or new parts of the application. And schema-based sync is where you would do that based on, say, schemas or tables like the DDL schema, and content-based sync is where you'd filter by the content, the rows in the database. And in a sense, what we've tried to do is we were well aware that we were biting off this challenge of partial replication with the application pattern that we're targeting, and so we wanted to try and design a system whereby you understand, say, the key touch points, and the key touch points are that there are certain things that you have to do in the database rules side, kind of in the DDL in our world. And that's do things like enforce certain data access rules and authorization. But beyond that, we wanted to give the front-end developer as much flexibility and expressiveness as possible to be able to craft applications that sync data in the right way, so that if you think about, for instance, like what subset of data that you're syncing, you might have selected a number of fields. You might want to tweak your user experience by actually syncing slightly more or controlling the kind of sync boundaries. And so we wanted to provide some primitives for the front-end developer to be able to basically control how data synced as they were binding it to their components. And so this sort of gives you an example of where we are. I was showing you that kind of Prisma-inspired syntax for the data access library that we have. So we have a similar syntax for basically defining shapes. And we have this shape-based sync model where shapes allow you to express exactly what you want to sync onto the device and how from a front-end point of view, and then kind of matches up with the server-side authorization. So in this example, it's showing, say, a simple project management app where, say, you've got projects who can have many issues, which can have many comments. And then on the right-hand side, it's saying, right, I want to sync, say, project ABCD, and I want to include all of the data that kind of comes in underneath that project, so that I know that once that set of that shape of data is synced onto my local application, I can interact with kind of all of it. So, for example, if you're building like a social design app like Figma, you could sync in a whole workspace or a whole design document at the same time, and kind of all the information would sort of come in at once, and you could then interact with it properly. Just at the bottom, you have the example of the retain configuration. So as well as defining kind of what you're targeting, the sort of shape of the data that comes in, you can also express the semantics around, do you want to keep that data live, for how long, what happens, for instance, if there's contention on the storage space on the local device. So there's basically configuration options for specifying that. And then sort of taking it kind of further into the sort of day-to-day of the front-end development. So if you think about a system like, say, GraphQL with Relay, you have it set up where you have like a fragment container that binds data to your components, and you have a component hierarchy, and then the Relay compiler basically aggregates out the different fragments into a top-level query in order to optimize the fetch for that kind of top-level query for a route. And what we've seen is we have an application where the components themselves are just interacting directly with the local database, but we can have a similar compiler step to basically aggregate out the shape of data that's required to sync onto the application in order to fulfill so that the right data is there for the components in that hierarchy to interact with. And so we have a React integration, and you have this sync shape component, and that basically defines a shape like a provider in a hierarchy, and then components down in that hierarchy, they can be sure that that shape of data is synchronized onto the local app before they're rendering, but also they can use handles to the filtered data to just work with data inside that shape. And then one of the other interesting challenges, again, with the pattern that we've been digging into, is if you're building applications, they typically have features like listings and search. And there are patterns, say, with shapes. If you had something like a shallow, wide shape where you could say, right, if I want to search projects, I could sync in just the name field or just the full text search index. But what if actually you don't want to sync in that kind of index data, or it's too large to sync onto the local device in order to be able to do search functionality? The kind of obvious solution is to go, well, for that we need to maybe go out of bound if we need it, or we don't provide that. But what we designed was a system where when you have online connectivity, you can submit basically register a discovery query. Where what happens is that the parameters of that are sent to the server. The query is run against the server-side database. We take the result set and turn that into a shape and maintain that in sync onto the local device, whilst also running code on the server side against the replication stream in order to update and add any additional listings to it that would have been included in the query as the data changes. So in a way, it's a way of basically doing arbitrary queries against a server-side database in order to then take the filtered result set and turn that into the data that's synchronized onto the application. And one of the key differences here is that with that approach, it's much easier to apply things like ordering, like sorting and filtering. So take the 20 most recent results, which are quite tricky to manage for just the kind of pure shapes. And it allows you to basically define queries whereby where here we have like where name search is foo or bar, that object which contains the search is foo or bar is passed to a user-defined function that allows you to execute then arbitrary query logic in the server-side database. I'm not quite sure how I'm doing on time, so somebody shout if I need to stop. But I'll sort of skip through this one. Yeah. So just briefly, I'll just get to one thing, right? So as we all know, that there's a lot of challenges operating on this kind of far AP side of the cap theorem. Obviously, the kind of area is becoming a lot stronger over time. In our case, with doing this for local first SQL, we have additional particular challenges around integrity, around how you maintain constraints and referential integrity. But then once you come to do partial replication, then that gets even harder because you're trying to maintain the same constraints across the replication boundaries. And so you have these challenges where you're saying, right, how do you replicate a row which, say, has a non-null reference as a foreign key to a table that you're not replicating? Or, for instance, if you're trying to do a write, and you're trying to validate either that it's a field is unique or that a reference is valid. And if you're trying to say write with finality on the client, so that if it's accepted on the client, it will be factored into the overall eventually consistent database, then how do you do that if you don't have the information available to validate it against? And so, I mean, there's a few approaches. The simple thing would be don't have partial replication boundaries, which is sort of one approach, but kind of rather limits your sort of control over sync in your data modeling. Another is that you replicate the minimum of the related table to allow you to have the information available to do what you need to do. And another is to lift the constraints out of, say, the pure SQL data model and find a different way to enforce them. So, for example, if you had a unique constraint, you take the constraint out of the DDL, but you then use a reservation system like a distributed locking system in order to enforce the uniqueness. And then if you're similar to kind of with the rights, and then the finality question is very hard, whereby if you're trying to write with finality, you need to make sure that you have exactly the same data as well as deterministic validation logic on the server and the client. And then building on that, there's also some fundamental trade-offs, I think, between a causally consistent system, which is typically the strongest mode that you can have for this type of local first system, and access control, whereby if in order to provide causal consistency, you allow clients to write in the past, how long do you allow them to do that for? And what's the relationship there between malicious users who are trying to act in the past? And there's a relationship there between how long you hold things open for kind of normal behavior, for instance, for just reconnections and data retention for reconnections, versus kind of at what point you might stop allowing somebody to make a write, which could still be factored in potentially weeks or months after an original transaction was committed. So anyway, I've skipped over these last two were meant to be a little bit more discussion-y, but I suspect I should finish. That's me.